Okay, so we are going to talk about particle motion today, and this is something I wanted to do in class and I had originally planned to do in class, but because of the asynchronous day, we can't. So I am going to extend the homework. The homework was set to be due tonight. I'm going to make it due Sunday night. That way you guys have enough time to email me if you have questions or to attend one of Mr. C's sessions tomorrow. I'll have Mr. C kind of work on this tomorrow because it is a new concept for a lot of us, and it's going to kind of be a little bit different. It connects to derivatives, but it's definitely kind of a new twist on it. And if you've taken physics before, that's really great. I would recommend that everyone, but especially those of you who haven't taken physics, watch the 2-minute video that I posted as well before watching this, because it's just a little bit of a primer. This is something that we're probably used to in our everyday life, but we're not used to connecting it to calculus. So just kind of to recap is we are going to be talking about position, and in physics, if you've taken physics, they use the word displacement. Displacement is the exact same thing as position, but in calculus we use position. Then we're also going to be talking about velocity, and we're going to be talking about acceleration. So position is essentially where you are, but it's what we call a vector, and a vector has a direction. So with position, right, we might be talking about the x-axis. So if we talk about the origin, right, that could be like your house, that could be whatever starting point you pick, right? Your position could be, you take maybe 2 steps to the right, so maybe you're right here, and so your position is +2. But you could have also taken 2 steps to the left, and then your position would have been -2. So that's when we discuss position, it's talking about where are you compared to the origin. There is another word called distance that once in a while we will talk about. And what distance is distance is a scalar, meaning, right, these were vectors, meaning they have a direction, right? So +2 meaning like 2 to the right, or -2 meaning 2 to the left. Distance is a scalar. It has no direction. So what distance essentially is distance is essentially in a way, it's the absolute value of our position. So distance would kind of be your overall, if we were talking about steps, like your overall steps or your overall, like, position that you've moved. So when we talk about distance, if I was here, right, if I just went straight from the origin over, my distance would be 2. Not +2, not -2, just 2. If I went to the left, my distance would also be 2. Not +2, not -2, but just 2. If instead we kind of think about maybe a new situation where, I'll use red, maybe I start right here and I take 1, 2 steps to the left. Right now at this point in time, my distance is 2, but my position is -2. Then if I walk backwards and I take 2 more steps back to, be at the origin, now my distance that I've traveled is 4. I've gone 4 steps. But my position is 0 because I'm back at my starting point. And maybe I go 2 more steps over to the right. Now my distance is 6. I've taken 6 total steps, but my position is only 2 because I'm only 2 to the right. So that's kind of how distance works, right? So position is where are we compared to the origin, whereas distance is how many overall steps or what overall position have I moved, right? Then when we talk about velocity, velocity is going to be our change in position divided by our change in time. And it's a rate, right? We've kind of talked about this hopefully in 8th grade math, right? The rate is your distance over time, right? We're going to call this position over time because we're going to have a velocity as a vector. So velocity always has a direction, right? If you're in your car, you might be going 65 miles per hour going forwards, but you also could go in reverse and go 65 miles per hour in reverse. That would be a little scary to go that fast, but you could, right? So velocity is basically your speed, but attached along with it is a direction. So it's, that change in position, not your change in distance. So our scalar for velocity is speed, right? Speed kind of matchups with velocity, and speed is our absolute value of our velocity. So we're basically just removing that direction. So this, you would see on your speedometer, right? That's in your car. They call it a speedometer. Is that if you go 65 miles per hour in reverse, it's just going to read, here's 0, maybe 65 is over here. It's just going to be reading at 65. If you go 65 in reverse or in forward, it'll still go to 65. It doesn't matter. But your velocity is different. You're going 65 forwards or you're going 65 backwards. Maybe you jump on the 5, right? You're on the 5 north or you're on the 5 south. You're going to end up at a different spot. Speed doesn't care about that direction. It just cares about the number. Okay. And then acceleration is a vector. There is no scalar that we attach to acceleration. So acceleration is our change in velocity divided by our change in time. And so in the video, he talked about, you could be not moving and accelerating. Basically, if you just stand and just start spinning in a circle, you're accelerating because you're changing your direction, right? Now, normally, when you accelerate, you will be also changing your speed and your velocity. But we do want to be careful about this because when we talk about these positives and negatives, they can get a little bit tricky. So I kind of want to talk about, hey, maybe, you're in a car, right? Here's the origin, and you start moving forwards. Well, if I just basically slam on, the gas, right? I'm starting off at 0 speed, and I just start increasing my speed. Then I'm increasing my velocity. I'm also increasing my speed. I'm speeding up. And my acceleration will be positive, right? But if, I get out to, somewhere and I realize, hey, I forgot, maybe I only went out like, 20 feet. And now I'm over here and I realize I forgot my keys and, my house keys. And instead of wanting to turn around, maybe I just go in reverse. And so now I'm going in reverse and I'm going backwards, right? So if I, again, start off at 0 miles per hour, but I start going backwards, my velocity is actually decreasing. And the reason my velocity would be decreasing is because I would be going backwards, right? I would be going like from 0 to maybe negative 20 miles per hour. So those numbers are going down. So my acceleration would actually be negative. Now my speed would be getting bigger, right? Because my speed would be going, it doesn't care if it's negative or positive, it would just be going from 0 to 20. So I would be speeding up, even though I'm, in reverse. So it is a little bit weird, but we just want to kind of think about that. And the key would be like, if you're hitting the brake, you would be slowing down. If you're hitting the gas, you would be speeding up. That part's obvious. But the velocity, it does depend on which direction you go, right? If I just kept going backwards, right, and I keep going negative, my velocity is decreasing, but I'm still holding down, I'm still hitting the gas, right? But my acceleration is negative, which is kind of weird. If all of a sudden I started braking here and I started kind of slowing down, right? Now my velocity would be increasing even though I'm going backwards, because I might be going like negative 20 miles per hour, negative 10 miles per hour, negative 5 miles per hour, 0 miles per hour. And so I'm hitting the brake, and so my velocity is increasing, my acceleration is positive. That's all a little bit weird. If that's a lot for you to take in, maybe try just rewinding and watching this one more time. And the more we practice it, the better we're going to get at this. So jumping into the actual lesson is we're going to deal with either the x-axis or the y-axis in calculus. So nice and easy, one direction, left and right or up and down. So we want to kind of think that up and to the right, we're going to always define as positive. So anything we're going up or anything we're going to the right, we're going to define as positive. That means down and to the left would be negative. So when we think about those, we are going to define these as functions. We're going to give them, equations. So we might say that the velocity is equal to like 4.9 times time squared, right? We're going to give it a function. Now, even though we're going to graph these, the particle's not going up and down on our graph. So if you have a graph of 4.9t squared, that graph might end up looking like this. But our particle's just going left and right on an axis. So the upwards motion means that it's going more and more to the right. So usually we're going to think about the x-axis for this chapter. We'll use the x-axis, and later on we'll move on to the y-axis. So we're going to start with the formula for velocity, and we'll do average velocity and instantaneous velocity. This is a lot like the average rate of change and the instantaneous rate of change, right? Velocity, we said, was essentially the rate of change of the position. That's what velocity is. It's the rate of change of the position, right? It's your change in position divided by your change in time. That's kind of like change in y over change in x. So when we have average velocity, now we're always going to need average velocity. We're always going to need an interval. So maybe like from A to B, right? So our average velocity formula is going to be the position at B minus the position at A divided by B minus A. And so we'll kind of define that X is our position equation. Sometimes textbooks or problems will use X. Sometimes they'll use S, the letter S. That's actually a very British term, but some of them will use S. And some of them will use P for position. So if you kind of see X, S, or P, they're probably going to be talking about position. The questions will make it clear, though. They're not going to make you guess at it. Okay, and then our instantaneous velocity, that formula will just be equal to the derivative at some point. We'll call it c. So the derivative at some point, that's going to be our instantaneous velocity. So again, this is very similar to our average rate of change and our instantaneous rate of change. So in this example, it says a particle's position is given by the function p of t equals e to the t times sine of t, where p of t is measured in centimeters and t is measured in seconds. So p is in centimeters and we have seconds. And so kind of just a little side note, if we want to kind of think about this, is position, our units for position are always going to be just whatever units there. Maybe it's meters, centimeters, you can fill it in. So I'll kind of put an M here, but it could be feet, it could be inches, whatever. Then for velocity and for speed, both of them, our units will be those same units per a unit of time. Right? So those same units per a unit of time. And I didn't mention distance, but distance also would have been the same as position. Right? And then acceleration are going to be our same units per a distance of time squared. So like meters per second squared, or feet per second squared, or miles per hour squared. Okay? So that's just a quick kind of primer on the units. So here, average velocity, right? Our formula is going to be, I'll use p because they gave us p, but it's the same as x, right? P of 3 minus p of 1 divided by 3 minus 1. Now this is a calculator question, right? We have e to the t. So you guys can, pause this video if you need to and pull out your calculator. And so we're going to type these into our calculator and get the answer. You can do this all in one step. You can do it in multiple steps. It's totally up to you how you use your calculator, as long as you practice making sure that you use it correctly. We are going to start using calculators on our tests. And on the final, we are going to be expected to be able to use our calculator. So kind of going into here, let me adjust this for us so we can see it a little bit better. Usually what I do on these is I just type in that equation first. So e to the, now you can use time or you can use x. A lot of times I'll change it back to x, but for right now I'll use time. So e to the t times sine of t. The advantage to using x is if you use x, you can graph it, right? If you use t, you can't graph it. You can't go over to the graph. So e to the t times sine of t, and we want to do this at, right? And we've done this with x. You can do it with t. It doesn't matter. It can be t or x, as long as your variable is the same. So at time equals 1. Now I know whenever I have sine, it's just going to tell me sine of 1, so I'm going to hit Control Enter to make sure I get a decimal. And I'm going to do the same thing at time 3. I'm going to hit Control Enter to make sure I get a decimal. And so then now let's plug in that formula. So p of 3, that's this one, minus p of 1, that's this one. I just kind of go up and hit Enter to bring them down so I don't have to retype them, divided by 3 minus 1. So that's our formula, and we get 0.27355. So if I round it, 0.2736, right? We always want to go to 4 decimals. So I'm going to say this is equal to 0.2736. And now we need units, indicate proper units. So what were our original units? They were centimeters. And we want to remember anytime we do a rate, which velocity is a rate, we add on a per time. So centimeters per second. You can also just kind of memorize that velocity is units per time and acceleration is units per time squared. Okay. What is the instantaneous velocity? So instantaneous velocity just means to take the derivative and plug it in. So we're going to do p prime of 1.5. All you have to write out on your homework is actually that, or on a test, right? And then you do it on your calculator. So what we're going to do is we're going to do this derivative button. And again, this is something you definitely want to practice. I'm going to do time, but like I said, if you did x, you can do x. And I'm going to come up here and just kind of grab this guy, pull it down. And outside the parentheses, always outside the parentheses, control equals at time equals 1.5. And there's that. You could have done this in 2 steps, right? You could have said, let's find the derivative first. And that's my formula for the derivative. And then you could have plugged in here at time equals 1.5. And you'll get that same answer of 4.78. I like to do it in 1 step, like this guy. But if you want to do it in multiple steps, that's okay as well. So 4.875 if we round it. 7875. So 4.7875. And again, it's a velocity, so our units are going to be the units for velocity, which in this case are centimeters per second. So hopefully that's not too bad for us, right? Kind of practicing using our calculator. So now, before we move on, we do kind of want to make this connection, is that if, we were kind of thinking that slope of the secant line, right? We talked about that as average rate of change. We said that was f of b minus f of a over b minus a, and that's going to kind of match up with our position at b minus our position at a over b minus a for these particle motion problems, right? So that's our average velocity from a to b. And then we had said that, kind of similarly, the slope of our tangent line right, that was equal to f prime at some value c. And so that's going to kind of match up with this x prime of c, our derivative of our position, which is our instantaneous velocity. So that should be obvious, but I just want to kind of add it to our notes just to make sure we really have that down. Okay, so now we're going to move on to the average and instantaneous acceleration. Okay, average acceleration isn't too common, but it does get asked. So the average acceleration, again, you always need an interval. So our average acceleration, on the interval from a to b will be equal to, now this is the velocity of b minus the velocity of a over b minus a. And this is because acceleration is kind of defined as the rate of change of our velocity. So that's the definition of acceleration, is the rate of change of our velocity. Okay. If you've taken physics, you'll kind of recognize some of these formulas written in different ways. Right, in physics, you might have had the formula like A equals VF minus VI over time. And really, that's the change in time. And so VF is VB, VA is VI, and then the change in time will be B minus A. B and A are times, right? They're times for particle motion. So that's kind of just that connection you can make. So, here's this formula. And then our other formula will be our instantaneous acceleration. And we're actually going to almost kind of have 2 formulas for this one, right? So it can be equal to V prime of C, But it also could be equal to the second derivative, I'm going to use x here, of position. So it's either the first derivative of velocity or it's the second derivative of position. And that should make sense because, right, it's the derivative of the derivative, which is the second derivative. So there's that. So a particle's position is given by that same function, p of t equals e to the t sine t, where p is in centimeters and t is in seconds. What is the average acceleration between time 1 and time 3? So we get our average acceleration is v at 3 minus v at 1 divided by 3 minus 1. Now on our calculator, we don't have the formula for v. We have, e to the t sine of t, but we kind of did this, and if you haven't, just you can enter this line without the at. So the derivative is e to the t cosine of t plus e to the t sine t. So I might even write that out just to kind of help me out, is that v of t, that formula, would be e to the t cosine of t plus e to the t sine of t, right? That's our formula for v of t. Now what we can do is we can say, okay, let's define this control equals at time equals 3. Right, I'm going to do control enter to get a decimal. I'm going to do it again at time 1 and do control enter to get a decimal. And then our formula was, right, v of 3, that's this top one, minus v of 1, that's this guy, divided by 3 minus 1. So we get negative 10.4031 if we round it, 4031. So negative 10.4031. And then we want proper units. So our units are always, for acceleration, our distance per time squared. So centimeter per second squared. Right, if you've taken physics, hopefully those units are familiar to you, like meters per second squared. Right, and what does that negative mean? That negative means that we're decelerating. Now, our velocity, here, our average velocity was positive, but we're slowing down. So that means, the negative means we're slowing down. So you might be going forwards, but you're slowing down, and then eventually you might start going backwards. Actually, that is what happens here. Because if you see at time 1, we were going forwards at 3.75 meters per second or centimeters per second. So like if you were traveling, like if you were an ant, you were going forwards and you started slowing down, you would have stopped, and then you started going backwards, and you start going backwards more, faster and faster and faster. So that's kind of what's happening. So what is the instantaneous acceleration? So we can either write this as, essentially the acceleration at 1.5 will either be equal to v prime of 1.5, or we could have said that the acceleration at 1.5 will be equal to x double prime of 1.5. It's kind of the same thing, right? So we're taking the derivative twice. Now, we already did take the derivative once, right? And we got this e to the t cosine of t. So now we're going to take the derivative of that a second time, and that's when we're going to plug in 1.5. So you can do this in one line if you feel really good about it. Is you can do outside the at t equals 1.5, or you can do it in 2 lines. So that's my second derivative, and this formula would actually be the formula for the acceleration. So just kind of as a side note, acceleration of t, that formula would actually be equal to 2e to the t cosine of t. Right, this would be at any time. But we don't want it at any time, we want it at 1.5. So we're going to plug in 1.5. So we can take this guy and plug in at 1.5. Now be careful on these. You only want to plug in when you're doing that. Oh, I forgot the t equals part. You only ever want to plug in when you're doing that second derivative. So you would want to plug in on this line, but you don't want to plug in on the first line, because then if you took the derivative of that, you're going to get 0, because you would have already had a number. You would have already had a constant. So you could have also put the at time equal to here, right? Because that's the second derivative. That's the derivative of velocity. But you can't do it when you're plugging in for the derivative of the position. If that, hopefully that kind of is clear. Right, so this we would have gotten the same answer. Right, so 0.6340. We are going to put the 0 in there. That tells the grader that you know that it keeps going. So 0.6340, and then centimeters per second squared again. Okay. So moving on, we're going to kind of just connect this back to like f of x. So f of x kind of corresponds with our position. Then f prime of x corresponds with our velocity. And then f double prime of x, our second derivative, corresponds with our acceleration. And so eventually we will make some connections with these, right? If we have like a graph of the position, that means that increasing and decreasing, right, the derivative, increasing and decreasing, would be the velocity. And concave up and concave down, the second derivative would match up with the acceleration. Okay, just kind of as a side note, right, we have speed is that scalar version of velocity that doesn't have a direction. And distance is that scalar version of position that doesn't have a direction. We will talk about these a little bit. So we had this table from before, right? We've used this table, but now we can just kind of change, okay, velocity is f prime of x, and position is f of x. So what did we say when the derivative was 0? We have a critical point, right? And that's where we could have a maximum and we could have a minimum. So what does that mean about the position? That means that the position can change, like directions at this point, and maybe also, the position can have a max or a min at this spot, right? It's our critical point. When f prime of x, when our was positive, that meant that our f of x was increasing. So this means here, when the velocity is positive, that means that the position is increasing. And when velocity is negative, that means that our position is decreasing. Okay, and then when our velocity changes from positive to negative, what that means is that it means our position changes from increasing to decreasing. And so this would be, essentially a relative max for our position. And when our velocity changes from negative to positive, that means that our position changes from decreasing to increasing, and that would kind of match up with a relative minimum for our velocity. And we can also do this for acceleration, which, kind of f double prime of x, back to velocity is f prime of x. And literally everything that we wrote up here, I'm not going to waste our time, everything that we wrote up here, you can just fill in here, but just change the word position to velocity each time. Right? Because see how it's still, this f to f prime is one derivative, f prime to f double prime is one derivative. So you can literally just copy it. I'm not going to waste our time, just kind of copy it, but just keep changing the word from position to velocity. Okay. So kind of looking at a graph, it's very important when we see a graph to make sure that we look at what they give us. This one gave us the position. Like I said, sometimes they'll use S, but they gave us the graph of the position. So this is not the graph of the velocity. It's not the graph of the acceleration. It's the graph of the position. So this is time, and this would be position. They're calling it S of t. So what we know is at all of these points, A, B, C, D, and E, our position is to the right. So, if I had a number line, right, and this was like our starting point, at A, we're somewhere over here. At B, we're somewhere further over here. At C, we actually went back a little bit. That's why it goes down. At D, see how D is just a little bit above A. So at D, we're just a little bit past A. And E is definitely past C, so E is somewhere way off to the right. So that's kind of what this is saying. So when it's going down, it's just going left. So, right, we went, we don't even see where 0 is, but we went over to A. We kept going to B. Then at B we turned around, we went back to C and back to D, and then at D we turned around, and we went back over to E. So that's kind of the path of this particle. It's just turning left and right. So at which point is the velocity equal to 0? Okay. Now this is just like f of x and f prime of x. So when would f prime of x be equal to 0? F prime of x would equal 0 at B and at D, because that's when the derivative is 0, right? S prime of t equals 0. Well, S prime of t is velocity. Another name for, right, the derivative of position is velocity. So basically v of t, and we could say equals S prime of t if we want to, would be equal to 0 at B and D. They want us to justify our answer because the graph of S of t has horizontal tangent lines at those points, or horizontal tangents at those points. Right, you could have probably gotten away with saying it has a maximum or a minimum as well, but the horizontal tangent, that's kind of the better explanation. Okay, at what point does the acceleration equal 0? This one's a little bit trickier to find, but right, acceleration of t, how does that compare to s? That's the second derivative of t. So we want to know, when does that equal to 0? Well, that equals 0 when we're changing concavity. So when we change concavity, so when we go between concave up and concave down, if we kind of look at this graph, it looks like it starts off concave down, right? And then somewhere, looks like right about C, it changes to concave up. So it looks like C is where it changes concavity. So that would be where S double prime of t equals to 0. Right, when you're looking for inflection points, you're always looking for kind of these spots where it looks like it's kind of starting to look like a straight linear line, like a y equals x or negative x. It's kind of in between those concave up and concave down sections. So that happens at point C, and that's because S of t changes from concave down to concave up at that point. So it is, C is an inflection point. All right, on what intervals is the particle's velocity positive? So, velocity being positive, that's the derivative. That's going to match with position increasing. So where is this position increasing? So it's increasing, right, up until B, and then from D going forwards. Don't put from D to E, right? There are arrows on this graph. Whenever there are arrows on this graph, you're going to use infinity. So the velocity is positive for negative infinity to B, right, because we have arrows, union from D to infinity. Sometimes they won't use negative infinity. They'll start off at 0. They'll say like 4 time is greater than 0 or equal to 0. And so then instead of using negative infinity, you would use 0. And that's kind of because negative time doesn't make a whole lot of sense. But what negative time would just be the past. So in this case, they didn't tell us that it starts at 0, so we'll use negative infinity. But just be aware that on a lot of these problems, they do say time is greater than or equal to 0. Okay, and so why? Because S of t increases for those intervals. Okay, where is the velocity negative? This would just be where it's decreasing, so kind of the opposite from B to D. So V of t is negative for B to D because S of t decreases for those intervals. On what intervals is the acceleration positive? So positive is going to match with concave up. So where is this graph concave up? We said C is the inflection point, so it's definitely going to change at C. Right? So I'm going to kind of look at C, and it's concave up to the right of C, so from C to infinity. So A of t is positive for C to infinity, because S of t is concave up for those intervals. And so we always want to connect it to the graph that we have, right? I know sometimes you guys say like because S double prime is positive, like F double prime of X is positive, or because F prime is increasing, right? You always want to connect it to the graph we have. So we have the graph of position, right? And we know that position is to get from position to acceleration, right? Acceleration is the second derivative of position. So that's why we're saying since we have position, then it's going to be the concave up or concave down, right? And then flipped acceleration is negative, then for negative infinity to c, because S of t is concave down. So again, this is something where it is a totally new concept. If you need to rewind it and rewatch this, I would definitely recommend doing that. Because it's just so new and so different for us. Okay, so we're going to kind of talk about 5 key principles here. I know we're throwing a lot at you. I'm throwing a lot at you in one day, but I am going to give you the whole weekend to practice this. I just want to really make sure that we're talking about all of this and that we're really trying to understand this and see it, and then we'll start to get the practice. So again, this is particle motion. In this case, we're talking about a particle that's moving along the x-axis. Right, and so in calculus, we always use a particle because particles don't have to worry about friction. They don't have to worry about wind resistance, air resistance, anything like that. We're just really just talking about the motion going left and right. So our first commandment will be if the velocity is positive, then our particle is moving to the right. Then kind of vice versa, if the velocity is negative, then our particle is moving to the left. All right, next up we have speed, and we haven't really talked about this one, but this is a little bit trickier. So the particle speeds up, that would mean the speed increases if the velocity and acceleration have the same sign. And I'll talk about this in a minute. So meaning either the velocity and the acceleration are both positive or the velocity and the acceleration are both negative. And then kind of the opposite of this would be the particle slows down. Right, its speed decreases if the velocity and acceleration have opposite signs. So one is positive and one is negative. And so if we just think about rule 3 and 4, right, this is a question that is kind of common on AP free response. They'll ask you, is the speed increasing or decreasing? Or they might say, is the particle speeding up or slowing down? And so kind of if you just kind of think about, being in a car, right? If you're in a car, here's my beautiful car, and you start moving forwards, right? You put on the gas, you're moving forwards. Your velocity is positive, and you put on the acceleration, right? You're going faster and faster and faster. You're like slamming the gas, right? So you're going 0 to 60 miles per hour as fast as you can. Your velocity is positive because you're going 0 miles per hour, 10 miles per hour, 20 miles per hour, 30 miles per hour. Your acceleration is positive because your velocity is increasing. You're putting down the gas, right? So in this case, they're both positive, and we would be speeding up. Well, if we think about a new situation, right, where maybe we're now going 60 miles per hour, so our velocity is positive, but we start braking, right? We start braking. So we're going 60 miles per hour, but we brake, right? Maybe there's a branch or something in the road, and we brake. We're going 60, 50, 40, 30, 20. Our velocities are all positive, right? We're still going forwards, but we're braking, so we're decreasing our velocities. They're still all positive though, 60, 50, 40, 30, 20, but we're slowing down, so our speed is decreasing. These are the two really obvious situations. The ones that are a little bit trickier are when we're going backwards, when we're in reverse. So if now you start going backwards, okay? So if I put on the gas going backwards, right, my velocities are all negative, okay? But this is where it gets a little bit weird, is if I'm putting on the gas going backwards, my acceleration will be negative. And the reason my acceleration will be negative, let's say we're starting off stopped, and we put on the gas in reverse. We're going 0 miles per hour, negative 10, negative 20, negative 30, negative 40, negative 50. The reason my acceleration is negative is because the change in velocity is getting more negative, right? Negative numbers are like negative 20 is a smaller number than negative 10. Negative 30 is a smaller number than negative 20. So if we're going this way, our acceleration is negative because we're getting smaller and smaller. Our velocity is negative because all those numbers are negative. But our car is actually speeding up here, right? Our car is going from, the speedometer would read 10, 20, 30, 40, 50, 60, right? It doesn't care about the negatives. It's the absolute value of those negatives. So the car, we would say that car is speeding up even though it's going in reverse. But we actually say it's decelerating, which is weird. You don't really think of that as decelerating. That's, but the acceleration is negative. Okay, and then our last one would be that now we're, negative, we're going backwards, but we hit the brake. So maybe we got up to like negative 60 miles per hour in reverse, and then we hit the brake. So our velocity is negative, right? Because it's starting off at negative 60 miles per hour. But as we brake, we're going to go negative 60, negative 50, negative 40, negative 30, negative 20. Those numbers are getting bigger, so our acceleration is positive. But what is our car doing? We're braking. Negative 60, 50, 40, 30, 20, 10. We're going to start braking and get to 0. So our car is slowing down. So we can kind of see that the slowing downs, right, they had the opposite signs. In the speeding ups, they had the same sign. So that's kind of the key to this. Okay, I know it's a little bit weird, but I did want to go over that. There is another concept that's very similar, and that's the particle moving to the left or moving to the right. And so if we kind of think about that on our number line, moving towards the origin or away from the origin. So if I was a particle over here, right, my position is positive. If my velocity is positive, that means I'm moving to the right. And so I'd be going away from the origin. Whereas if that same particle, right, was in that same spot, its position is positive because I'm to the right. But if I was going backwards, right, I would be going towards the origin. I'd be returning to the origin. And then on the flip side, if I was a particle over to the left, now my position is negative because I'm to the left. Right? The position being negative just means where am I? I'm to the left. So my position is negative, I'm to the left. If my velocity is positive, that means I'm going to the right. So again, I would be going towards the origin. Whereas if instead my velocity was negative, right? So my position's still negative because I'm over to the left. But if I was going to the left, that would mean my velocity would be negative. And so I'd be going away from the origin. So we can kind of see that this is again similar. If position and velocity have opposite signs, we're going to be going towards the origin. And if position and velocity have opposite signs, then we're going to be going away from the origin. So I didn't have this as one of the 5 commandments, but it is something you may want to add on, is kind of just, maybe just add it here. That's why this box is a little bit bigger, is the particle will move towards the origin. when the position and velocity have the same signs. Sorry, opposite signs. And away from the origin when velocity and position have the same signs. This has been asked a little bit more on recent exams, this concept of moving towards or away from the origin. So it's something that they've started to ask. They didn't ask traditionally in the past as much, but it's started to be asked a little bit more. A lot of times I used to recommend students to just kind of figure it out on the fly, but now because it's being asked more, it might be something that we want to add to a flashcard and kind of memorize. I would add all 5 of these to a flashcard and memorize them, maybe even add some more flashcards with this concept. So anyways, the 5th rule is that if our velocity is 0, and sometimes they'll say that means the particle is at rest. So if our velocity is 0, but the acceleration is not 0, right? We said that's when we can be changing directions. Right now, the particle might not change directions, but it definitely can change directions. So we're going to say the particle is momentarily stopped. And I'm going to say is likely changing directions. Now, the reason it doesn't have to be changing directions is it could stop and keep going, right? But essentially what's going to happen here, you don't have to draw this in. I'm going to just kind of draw first. So we're in our car, right? Maybe we're going forwards, and we start slowing down. So I'm going like 60 miles per hour, 50 miles per hour, I'm braking 30, 40, 30, 20, right? 10, and then I get to 0. So now I'm here, and we're momentarily stopped, right? And I've been braking. But if I'm still accelerating, right, or I have a non-zero acceleration, maybe what's happening is actually I stop, and now I'm going to start going backwards. So I'm changing directions, right? That might happen like if you're going to slow down, like if you're going to run forwards, right? If you're going to run forwards, like touch the ground at a point and turn back, like maybe a coach made you do that for like sprints. You're going to run forwards, hit a point on the ground, and run backwards. Before you can start running backwards, you have to stop. Your velocity has to stop. It has to go to 0. So you run forwards, you stop, and then you go back negative. So that's what that means. Now, could you technically go forwards, stop, and then keep going forwards? You could. So that's why I said likely changing directions, right? There is, the possibility that you basically just slowed down to a stop and then kept going forwards. That can happen too. But most of the time, that means that we're changing directions. So suppose the velocity of a particle is given by the function v of t equals t plus 2 times t plus 4 squared. And we want to find the values of v of 3 and v prime of 3. And based on those, describe the speed of our particle. So v of 3 is going to be nice and easy. We're just going to plug this into our calculator. So v of 3, we would do t plus 2 times t plus 4 squared at time 3. So parentheses. Then I'm going to do Control Enter just in case I have a decimal. Probably don't here. So we get 245. Okay, and we do have units here. So they gave us the units where t is measured in minutes and v is measured in inches per minute. So this is v, so we're going to do inches per minute. Okay, now v prime of 3, we're going to take the derivative and plug in 3. So we will do the derivative. I'm going to use time again. And then I just want this part. I want the at outside of the parentheses. The at needs to be outside of the parentheses. If you accidentally put it inside the parentheses, you'll get 0. So the at time 3 needs to go outside the parentheses. And I get 119. Now, we took the derivative. So instead of 119 inches per minute, we're going to have 119 inches per minute squared. And that should make sense because what is the derivative of velocity? It actually is the acceleration. So that v prime of 3 is the same as the acceleration at time 3. So now we want to describe the speed of the particle. When they ask us to describe the speed, they're asking us, is it speeding up or is it slowing down? So because they're both positive, we said when they're both positive, the particle will be speeding up. So we'll say the particle is speeding up at time 3. Because, and I like to just kind of say v of t is greater than 0 and a of t is greater than 0. Right, they have the same sign. If you want to kind of put same sign, you can. But I always like to do greater than 0 or less than 0. That kind of helps out. Okay, next one says, on what intervals is the particle moving to the left? So this kind of goes back to our rules, right? If the velocity is positive, we're moving to the right. If the velocity is negative, we're moving to the left. So this is very similar to what we did with increasing, decreasing, right? And so increasing, right, position increasing is moving right, position decreasing is moving left. So we want to kind of remember that. So with increasing, decreasing, we would take the derivative and set it equal to 0. What we need to remember here, though, is that the velocity here already was the derivative. So we're going to take the velocity, we're going to set it equal to 0. Right, that formula was t plus 2 times t plus 4 squared. You can use your calculator and the solve button if you really want to, but this one's easy enough to just see that it's -2 and -4. Right, so there's that. Now, it does then say, though, for time is greater than or equal to 0. So neither one of those actually fit. So we're just going to make our number line, and I know we've done one like this, we haven't done a whole lot like this, but basically we don't have any critical points. So I don't put 0 here, 2 here, I don't put anything here. I mean, I'll put a 0 on the end, but we don't put -2 and -4 because they're not greater than or equal to 0. So we can just plug in any number we want, right? We can plug in 1, 3, 5, 7, anything as long as it's bigger than 0. So if I plug in 1, I get positive, and I get positive. So it's positive. So this is always increasing, right? The velocity is always positive, which means the position is always increasing, which means it's always moving to the right. So you could say basically v of t is greater than 0 for all t greater than or equal to 0. So the particle is always moving to the right. Okay, so if we were given position, right, in this case we were given v of t. If we were given position, we would have just taken the derivative to get velocity and then set that equal to 0. So that's, where we get that moving left and moving right. So I know this was a long video. It was almost an hour long, but it's a lot of really important information and starting to make these connections. I know it probably seems really weird for you right now and overwhelming, but just rewatch this video if you need to. Go back and relook at some of this stuff. We're going to have 2 AP practice questions. I will have these in a second video where we just kind of talk about these more in depth. And then for homework, actually 3 AP questions, I forgot. For homework, you have day 43 homework. Some of these are pretty straightforward. This one starts off with the position. We want to know what p prime of 2 is and p double prime of 2 is and explain what those mean. Right? Are they the velocity? Are they acceleration? What are they? Then based on those values, what can we conclude about the speed? Is it speeding up or slowing down? And moving to the left or the right. Now remember, here though, we started off with p of t. So to get moving left or moving right, we're going to need to do p prime of t to get the velocity and set the velocity equal to 0. Then do a number line with that. Does the particle ever change directions? Justify your answer. That would be if it changes between, velocity positive and velocity negative. Then this one gives us a graph, and we want to think about on the graph. I will post the answers for these. Okay. Here, again, we start off with the position, and we want to know, is the speed increasing or decreasing? Now, they didn't ask us first to find the velocity and acceleration, but that's what you need to do. So you need to find the velocity at 2.5, the acceleration at 2.5, and see, is it the same sign or is it opposite signs? Then for 7, 8, and 9, we're talking about another position graph. What is the average velocity? So that average velocity formula. Then find the equation v of t for the particle, so take the derivative. And for what values will v of t equal 0? Set it to 0. Then you also have these two questions that are kind of from part of an AP free response. Find the acceleration when the particle is at 2. So they give you this formula. And then is the speed increasing at 2? So, plug in v of 2, plug in a of 2, see if the signs are the same or not. Then find all times when the particle changes direction. Okay, changes direction is going to be when v of t changes signs. So you're going to set v of t equal to 0 and then do a number line analysis. Okay, but we have an interval from 0 to 3. So just make sure on your calculator, right, you can set v of t equal to 0. But when you do that solve button, right, you're going to do solve, plug in the formula, equal to 0. You can do comma t, but then you need to do at 0 less than t less than 3. So that'll be kind of how you get your critical points there. Okay, so hopefully that helps out. Email me if you guys have any questions. You can also go to one of Mr. C's sessions. He has sessions tomorrow, I believe at 11:30 and at 1, maybe 1:30. I'll make sure he posts that.